So midpoint and distance in the coordinate plane is kind of a mixing of algebra and geometry. And we're going to see in geometry that the midpoint and distance formulas are pretty highly used. I mean, they're used quite a bit. So distance formula, I don't know if you remember what it was here. The distance formula is the following. I'll show you where it comes from here. If I can get this to work. Okay, there we go. So the distance formula is that d equals the square root of x1 minus x2 squared plus y1 minus y2 squared. And I can show you where that comes from. So suppose I have a right triangle. In a right triangle, we know that if we call this leg A, this leg B, and this leg C, that A squared plus B squared equals C squared, right? We know that. We know that, hopefully. Okay? In this case, what we're doing is we are saying that B is equal to y1 minus y2. And A is equal to x1 minus x2. And C is equivalent to D. That's all that we're saying. Think about it. Y1 minus y2, that's just taking and subtracting the y coordinates, the second coordinates, the vertical ones, to get that distance. And then x1 minus x2 is just subtracting the horizontal, the first parts of the coordinates to get the horizontal distance. So if I pop these in here and here, we'd have x1 minus x2 squared plus y1 minus y2 squared equals d squared. How do I get it to the final stage of the distance formula? There's a little algebraic step here. What do I have to do to each side of the equation to get rid of the square root? It's drawing the square root, right? So final step here is to take the square root of each side. And when I do that, out pops the distance formula. I'll give you a minute maybe to draw a picture and think about that. I could ask you to do this on an exam or on this chapter test. I may ask you to tell me where the distance formula came from, or to tell me the similarities between the distance formula and the Pythagorean theorem. So I'll leave that up there here for a minute. Yeah. I didn't really leave you enough room to write it down, but somewhere on there, I would maybe off to the side on example 1, draw this picture, and you should be able to go through this process, going from the picture and the Pythagorean theorem to the distance formula. A couple steps, and you should understand the similarities between the two. We use this frequently. So example 1 says find the coordinates of the midpoint with endpoints of A, -2, 3, and B, 5, -2, and the distance. So we'll get the midpoint formula in here as well. Midpoint formula is the following. Just x1 plus x2 over 2 and y1 plus y2 over 2. So it's finding the average between the two first coordinates, and then find the average between the two second coordinates. All right, let's see if we can do that. We've got example 1. Endpoint A is negative 2, 3. So keeping in mind that the x1 and x2 would be these two right now. I'm looking at those. I'm going to just pop them in to the first part of the midpoint equation. So it looks like this. Negative 2 plus 5 over 2. And then we got a comma. And then the other one here, these two, those are the y coordinates. So we're going to pop those in to the second part of the midpoint formula. So I've got 3 plus negative 2 divided by 2. And when I simplify each of those expressions down, I have the midpoint. This is something you could probably, I mean, instead of memorizing a formula, just think about the process. Yeah.
Can you just take away the plus sign because it's part of the formula? That would be 3 plus negative 2. So
3 minus 2. That's true. Yeah. What you can do is if you think of midpoint or middle between the 2 points is really average. The fact that I'm dividing by 2 here, and combined with the fact that there's always going to be 2 points, it means it's always the average. It's the average between these 2 points. So it's just finding halfway in between negative 2 and 5. Right? So instead of memorizing the formula, you can remember just the concept of midpoint. Halfway in between these two is going to be 1.5 or 3 over 2. And then halfway in between these two is going to be 0.5 or 1/2. So there's the midpoint. And then we're asked to also find the distance here. So let's take our distance formula. Did everybody get all this written down here? Do you need more time on this? Okay, so we're going to go ahead and calculate the distance here with these same 2 coordinates. Okay, so it'll look like this. D equals the square root. Now, we're going to do x1 minus x2. I'm just going to call endpoint A x1. So I have what I've circled in black will be my x1 and my x2. So I have negative 2 minus 5 squared plus, and then what I've circled in yellow there, we're going to call that y1 and y2. So I have 3 minus a negative 2 squared. And notice minus signs make a difference on here. Because I have a subtraction sign in the formula, I've got to be a little careful with my signs. So the first one is square root of negative 7 squared. And the second one ends up being 3 plus 2, or 5 squared, because of the subtracting a negative portion in there. So make sure you have both signs in there, the minus and negative. Makes a difference. So we subtract the x coordinates and square it. Subtract the y coordinates, square it. We're going to go ahead and square it at this step. Every time you square these numbers, whether it's a positive or negative, it will be positive. So we've got square root of 49 plus 25. Then you add the 2 together. Now we got 74. And in this case, we're just going to leave it square root of 74. If this is an applied problem, a word problem, something where, you know, I can't go out and buy square root of 74 feet of board or something for, you know. Well, if you tell them at Home Depot, I'd like square root of 74 feet, please, of duck fur.
I don't know.
A board about square root of 74 feet long will look too funny. But so then in that case, you would find your decimal approximation around this nuts, but we have a little room for error. But for these problems where we're just practicing the distance formula, just leave it like this. Yeah.
You would just have to ask.
8.5 feet, yeah, or just after 9, just whatever they sell closest to that. Or, I don't know, you could try, just go ask, can I have square root 74 linear feet of Bender board or whatever?
They'd be like, what is wrong with you?
Yeah. No, but it'd be so fun.
Yeah, it is definitely fun.
You guys are teenagers, you like to
Deal with
mess with
this.
people, right? All right, so example 2, I'm going to draw a picture first. So you can just watch as I draw a picture. I'm going to just show you, and you can decide later if you want to copy it down. But let me draw a picture and show you what we're doing before we go and do the algebraic calculation. So I've got, this time, a midpoint at 2, 4. We've got a midpoint at 2, 4. So let me go ahead and draw the 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Okay. So I've got a midpoint at 2, 4. So I'm going to go 2 right and 1, 2, 3, 4 up. So here's my midpoint at 2, 4. And then I've got an endpoint at negative 1, 7. So I've got an endpoint at negative 1, 7. That's R up there. There's M. So what I'm being asked to do here is to find the other endpoint. I am not finding halfway in between the blue and the red. I'm finding the other red point somewhere over here in this region. Okay? So a couple different ways to do this. We're going to do it algebraically in a minute, but I just want to show you. We're going to get the answer here just by picture. Okay? So if I start at R, I have to go down 1, 2, 3. Just check me on this. So I go down 3. You can see it here. And then I'm going to go over how many? I'm going over 1, 2, 3 as well. So if I go down 3 and over 3 again, I'm going to land at my other endpoint. So 1, 2, 3, and then 1, 2, 3. So somewhere over here, my graph, I don't know how accurate it is, but what did they want us to label this point? Remember, find the other end, we didn't say. Oh, RP. So this is P over here. But that's what we're doing by picture. We are finding the other endpoint there in red, point P, where this is, of course, the midpoint. So that's by picture. How would we do this algebraically using the midpoint formula? Because I don't know how accurate my little sketch is there, but any ideas? Yeah.
You set the midpoint to 2, 4.
Yes. So here's what he means by this. We have 2 parts of the midpoint formula. We've got the x1 plus x2 over 2. And what would that have to be set equal to?
That negative 1 plus x2 over 2.
Yes, it will become negative. But what am I setting it equal to? What is the x? So this is the formula for the x coordinate of the midpoint. So what is the x coordinate of the midpoint here?
4.
Or is the y coordinate? 2. So I've set this one equal to 2. And Grayson's right. I do know one of the coordinates, either x1 or x2. It doesn't actually matter. But I know one of the coordinates is negative 1. Okay. So that's one of the formulas. We'll have, it looks like this. It's going to be negative 1 plus x sub 2 over 2 equals 2. And if I solve for x sub 2, I find the x coordinate of P. The other equation I have, I'll do it maybe over here, y1 plus y2 over 2 has to equal what? 4, yes, because this is the y coordinate of the midpoint. So you have to know your definitions and exactly what these formulas do. And so y1 would be 7. So I have 7 plus y sub 2 over 2 equals 4. And then I'm going to leave the algebra up to you. If you could go ahead and solve each of these for x2 and for y2, would be great. Maybe I'll do one and I'll let you do the other. We'll do one. So we would first multiply each side by 2. We'd take and multiply this and this by 2. I would be left with -1 plus x sub 2 equals 4. And then add 1 over to each side. So x sub 2 equals 5. And so this coordinate has a first coordinate of 5, and then comma something. Go ahead and solve this other one, please, for me. Solve this guy. And let's see if it corresponds with my picture. Yeah. Get it? What'd you get? 1. Good. So y sub 2 equals 1. My picture actually turns out to be fairly accurate, right? So 5, 1. If you were working on graph paper, you could totally do this whole problem without doing any algebra. You could just count 3 down and 3 over from that midpoint, right? And that would be a viable way of doing this, at least as long as the other point is a integer point. It's not too far away. So that's midpoint and distance. It's going to be really important here. So you need to memorize this formula. You need to know how. You need to know these formulas. You need to know these formulas for yourself. All right. Any questions on that? If you want to draw the picture at this point, you could. I could leave that there for a minute. That would be helpful. From our constructions yesterday, look at example 3. From our constructions yesterday, what does it mean to have a ray like FH bisect an angle like EFG? What does that do? It bisects it, cuts it in half into 2 congruent angles, right? So you guys have something different on there, huh? Yeah, yours looks different than all. That does look different. Huh. Yeah, it might be. Okay, so you guys, it said you have ray FH bisects angle EFG, right? It says on there. Given that measure of angle EFG equals, pick an angle measurement for EFG. What could EFG equal? What do you think? 160. Let's go with it. 160 degrees. What are the measures of EFH and HFG? Then we're going to put in 160 as suggested here. 160, I think, is a good estimate of that. What?
So,
yeah.
If this kind of one problem works as any number back, would be for the number that's obtuse, that's obviously.
That'd be fine as long as you get the definition of bisector, right?
Okay.
They'll give you the angle though. This is kind of a wide open one here. But so each of the angles would be 80 degrees. That's the main idea. So on example 3 is they should each be 80 degrees. There's a bonus in there. And then there's another one in there about, I'll add it on to the end of this. I'll just draw it here. So yeah, that example 3 in your notes. You have a picture that looks like this. That's E, F, G, and then H is here. If this whole thing is 160, then each of these angles would have to be 80 degrees by definition of bisecting. All right, so your example 4 here, let's add this in as well. And then we'll do the ladder problem. It says using the diagram and the fact that RQ, here's RQ, I'll try to make it, well, that's not too great, but let's move that over just a bit. Okay, that's a little better. So we've got P over here, R is the vertex, S is somewhere over here, Q is up here. Now we're going to use some algebra to solve. So we got x plus 40, and we've got 3x minus 20, both in degrees. So it says using the diagram and the fact that RQ bisects PRS, solve for x. So what equation would we have this here? How would you set up what kind of equation would you set up? Yep. So remember, there's 3 different things you're going to do. Either equal to each other, or add up to equal 90, or add up to equal 20. Yeah, that's about it. Like over and over and over again. So x plus 40 equals 3x minus 20. Go ahead and solve for x for me, please. And then sometimes I'll ask you to plug that in and get the angle measurements. They don't here. So just find x if you could. And we'll look at our ladder problem. 30, x equals 30 is right. And you get to stop there on this one. Just read the problem carefully so you know what they're asking. All right, now we're ready for our ladder problem. Ladder. So this is example 5. So here we have this ladder, and we're going to place it up against the house. And the question is, do we need to go get a longer ladder? From the picture, yeah, we're landing midway. So it says, yeah. Oh, okay, maybe, yeah, we're just trying to get up to the window. So 20-foot ladder. Okay. 20-foot ladder is resting against the side of the house so that the base is 8 feet away. How far up the house is the ladder reaching? Draw a diagram. So my diagram would look like this. I have down here, we got here, we got here. There we go. Neon green shows up fairly well. This is 8 feet down here. The ladder is 20 feet. And then we are trying to find H, the height, up the side of that cool-looking house there. We land. So thinking about, let's think about the distance formula. Really, we're thinking about the Pythagorean theorem. We don't need to worry about x1 minus x2. I'm given x1 minus x2 right here. It's 8. So as a matter of fact, I could just think of this in terms of the Pythagorean theorem, okay, where so we've got C or D equals the square root of a squared plus b squared, so it looks like this. Oh, actually, I don't want to solve for that. That doesn't make any sense. Which one do I want to solve for?
H.
Yeah, I want to actually solve for H. So let's plug in what we know. We've got 20 is taking the place of C. 8 is taking the place of B, and A is our H. So how's that? H squared plus 8 squared equals 20 squared. Solve that for H, and we've got it. So we've got H squared plus 64 equals 400. We'll see how far up that wall that ladder actually did. H squared equals, is 8 feet away from the wall. Should be safe enough? I think it will be. 8 feet's quite a ways away. I don't think it'll tip over. So 400 minus 64 gives me 336. here it makes sense to go ahead and get a decimal approximation for the square root of 336. It makes sense here. So what's a decimal approximation for the square root of 336? 18.3 feet. So we're going to hit about 18.3 feet up the wall. So there's an application, real life application of the distance formula. Any questions on that?
The ladder isn't tall enough.
I was just talking about it, yeah.